Good afternoon, everyone. I'm Joanna Goldberg, a research informationist at Memorial Sloan Kettering Cancer Center's library. My colleague Robin O'Hanlon and I are thrilled to welcome you to Adventures in Text Mining, Applications, Ethics, and Cancer Care. We are joined by three incredible speakers today. Dr. Manika Lamba, Assistant Professor at the University of Oklahoma's School of Library and Information Studies, Dr. Anyi Li, Associate Attending Physicist and Chief of Computer Service at Memorial Sloan Kettering Cancer Center's Department of Medical Physics, and Dr. John Liu, Senior Investigator at the National Institutes of Health, National Library of Medicine's Intramural Research Program, Deputy Director for Literature Search at the National Center for Biotechnology Information, and Adjunct Professor of Computer Science at the University of Illinois, Urbana-Champaign. You can read their full bios via the link that I am about to put in the chat. Their presentations will be followed by a question and answer session. Please submit any questions you have using the Q&A feature and indicate who the question is for. This event is being recorded. The video, along with our panelists' slides, will be shared to all registrants after the event. We will be asking for your feedback at the end of the session and hope you can take the time to fill out our brief survey. And now, please welcome me in welcoming our panelists. Please join me in welcoming our panelists, beginning with Dr. Lamba.
Hi, thank you for inviting me. Let me share my screen first. So thank you for giving me this opportunity to talk to you today. So I'm just going to first briefly define my research, followed by 3 case studies from the research I'm has done or just going on with. So first one is on analyzing the topics in electronic thesis and dissertation. The next is on developing a web-based tool for text mining. And third is to where I'm trying to find the putting people first in data quality and using through the critical lens of feminist data ethics. So my research is typically in the intersection of HCI, knowledge organization, and right now I have a growing interest in critical data practices and AI in society. So these are the 3 highlighted papers which I'm going to talk to you about today. So the first one is analyzing the trends in electronic thesis and dissertation over the 100 years, taking a case study of library information science thesis. So the research questions were, how can we navigate the plethora of theses in the ProQuest thesis and dissertation database to find the relevant ones? How can we create an efficient recommendation system? What are the various access points available for discovering the thesis? And is there an established taxonomy, and is it comprehensive? So the ProQuest have these subject categories in which you can see that for library information science, they have these 2 code number, and can we they're just classifying the thesis based on these 2 tags. So can we further categorize them, or is there only 2 tags, right? We know library science is much more diverse. There's just tagging that with library science or information science. So even though I took the thesis from 1900 onwards till 2020, I found that only the thesis after 1950 onwards were having abstract, and before that they didn't have abstract, and my analysis included the analysis of abstracts to determine the topics. So in total, I end up with 4,574 theses, which had abstracts. And then determine the metadata quality. They were in inconsistent format. They had lots of incomplete metadata fields. So if our user want to search their database, they weren't able to find the thesis if they search by maybe departments, because 70% is missing, right? Or the advisor. So we need a different point of access to search the database, and this is where my research helped in. So I did topic modeling. That this is the overall methodology, like data collection followed by descriptive analysis, qualitative analysis, EDA. But here in my talk, I'm going to just focus on topic modeling and predictive modeling. So what is topic modeling? Topic modeling is an unsupervised machine learning text method which infers the topics based on the similar patterns. Okay, so for example, you have thousands of news headlines, and once you do topic modeling, it will give you, it is a kind of a soft clustering. It is different than your typical K clustering. So here it will try to find the hidden latent methods in the your corpus of data and then put them in different clusters. Yeah, so in my work, I use BERT topic algorithm. Uh, so it is a neural network algorithm where this slide is just showing the like how it works, and it was developed it is a very recent one which was developed in 2022, and even in this year they added one more layer of fine tuning, and around I think in around April, where now after you do BERT topic, you can also use large language models. You can use large language models to further fine tune your results. So the BERT topic is great. It does much better than your typical topic modeling algorithms like LDA, NMF, and CTM, and it provides significant flexibility in usage and fine tuning. But weakness is it assumes that each document consists single topic, and it doesn't reflect the reality of the documents that it may contain multiple topics. So after my analysis, I did find there are like much more levels to library science information science, and through topic modeling, I was able to even add one more within the toxicology. I would able to find one more third level, which is like archival study, and in the fourth level, I would able to find all the subtopics on which the thesis were, and like give the recommendation to add a topics as an access point of to databases like ProQuest or for your internal library systems. But what about the future ETDs? How can we use this topic model results for our advantage? Here where you can use machine learning. And as we already have the topics, and I do also divide them into broader categories of library science, information science, and archival studies, I tried few different classifiers out of which sport vector machine performed the best and gave it good accuracy. And then I built this dashboards. Maybe quickly I can show you. Let me see. Can you see the screen?
Yes.
With the dashboard?
Yes, so you can see the dashboard.
Okay, so I built this two dashboard. First is on just your metadata work, okay, and then the another one is just telling you about the topics. So here you have in like doctorate thesis or master thesis, you can go through the particular I'm just interested in archival study, I click on it and I look all the different researcher works, and then over the time then you can also download it through the data frame, like just you want to go through it, right? So maybe information science, doctorate thesis, I can download a copy. And then, just a second. And if you can also predict the category, right? So you input your own data file and then it will give you that. So just very quickly, I wanted to show you that. And then I also published a book on text mining for information professionals in 2020 in Springer, where you can just go through, like, there are all the case studies for topic modeling and other techniques by like step by step. You can go through them, and also there is a virtual interface where you don't have to even download our studio. It gives you out of box tool and our version of how to do perform these techniques. And this link it has a GitHub repo and a personalized the other website also, where in the GitHub repo also like update all the dataset where you can freely like use it for teaching practices or just explore and learn the techniques. Okay, sorry, why it's not showing. So okay, so topics model do not model topics. Like they have some ethical problems. I will not say ethical, but technical problem that does make unrealistic assumption. It is non-deterministic. It can't effectively validate against reasonable number of competing models, and it doesn't lock into well-defined linguistic interface. And it does make interpretation which are like have like human biases towards the patterns which we want to see, and also like something called apophaenia, which is the human tendency to perceive the elements in a meaningful pattern. And even though that it is possible that, but you still like the partial validation, but for the conceptual validation you still have to go to other methods and human ratings. So it's not like very perfect method like any other method, right? Coming to my next work, which is developing a web-based application tool for textual analysis for librarians, social scientists, or humanities. This work was done with collaboration with Faisal and Crescenda, who both are librarians, and John Stephen Downey, who was my postdoc mentor at UIUC. So this is the web-based tool which me and my team developed to do NLP, to do text analysis on bibliographic data. And let me show you again very swiftly. So this is how the app looks. It has a home page. Here you can, we provide you like few samples, sample file which can you download, or if you have your own file, just check it like it is in like readable by the dashboard which we created. Then you go to start analyzing, and then you have all this. So you can do topic modeling, like what I did. So this the whole interface is using Python at the back end. You can do keyword stemming, sunburst visualization, and all those different kind of visualization like burst detection, scatter text, and all those things. And yeah, that's it. So we develop this. So they're like it uses algorithms like topic modeling, or you can do text processing, and you can do different visualization. We deployed it on Hugging Face Space, and here you can export files from Scopus, Web of Science, Lens, and also if you have your own personalized CSV files. My last study, which is on like putting people first in data quality, looking through the lens of feminist data ethics. This work is in collaboration with Dr. Karen Rickett at UIUC and our fantastic RA, Jared Newman, who was a master's student at that time, now a PhD, doing PhD at UIUC. So in this work, we were so first, let me tell you what is critical data modeling. So critical data modeling uses tools to analyze the information system, connecting social critiques to the structure of digital information system and data objects. So in this work, we are trying to say that how open data sets like government data set are much more biased towards certain people, right? So here we are looking through the lens of critical data modeling, and every data model, it takes a position of what information is essential and which can be discarded, right? And these choices can influence your information system, and these choices can also impact the people and community. So we assess the traceability, completeness, compliance, and understandability of the LAPD dataset in our case study, and we did identify biases and systematic inequalities in the open government datasets, and there was an accountability which we think should be there for people, whereas right now the data set is more into like towards the institution and not for the communities, and there's a need for center for people and the communities in the data quality assessment. So first we did data profiling. So we are continually downloading the open data set, and we did an analysis on a version of the data set which we had from 2023, consisting of 23,840. 238,473 rows or cases, and we went through the age section and the race section, which they have, and we identified, we only focused on the ages which were less than 15, so basically children, and also for the racial and ethical groups, they have like 19th code, and we just saw that there is a racial disparity in arrest, and that it is not feasible to use this data set to pursue accountability for how police were interacting with the member of all racial and ethnic groups in the community. So what we found that the descendant codes were not aligning with the race and ethnicity categories used by the city of Los Angeles or the United States Census Bureau. For example, for the Asian which were represented in the arrest code were like 0.5%, whereas the whole estimate of the Asian descendant was like 12% of the total population. And then for the Black community, the total arrest was like around 27%, whereas while the Black and Los Angeles makeup was 8%. So how there are more than 3 times arrest in that sense, right? And then regarding the age, we examined the individual under the age of 15, and the charges of these children were from 0 to 13. 13 was like non-criminal detention, means like the children were not suspected, but they were just at the crime scene when their parents or guardian got arrested, and because the home was not deemed fit for these children, and they were referred to the social services, and but within the data record they were like they were in those record, means it's on their permanent record. So if somebody used this kind of data set for machine learning or predictive models, this can lead to misleading interpretations. And again, coming to the location, so they have assigned like crime incident occurred. So typical, mostly for the children from age 0 to 9 or from 13, like for 0 to 9 there were like blank charges because they were taken for by social services or somewhere, and that is like 63-64% of the records. So but they were giving a, until you do filtering, you can't find out that what was the purpose. So, the data can be falsely represent the criminal activity in certain location. So our proposed solution was to incorporate feminist data ethics and ethics of care for data quality assessment. Gray and Witt proposed the foundation principle of machine learning, which we think it's very useful to look into that sense in the grounded in the ethics of care. That is to critically evaluate the positionality, centering the human subject at every stage of the machine learning pipeline, and implement the transparency and accountability measures. Also, we give a definition of data quality, which centers around the well-being of the subject, which includes, which is like a data set should be a high quality data set. Can be considered high quality if the documents in its subject is attentive, responsive, and respectful manner. The object documents itself sufficient to detail the enable accountability of the institution towards the committee members, and that they protect the interests of children and other vulnerable people about the institution needs or efficiencies. So these are my upcoming books in next year, hopefully. One is on introduction to topic modeling and topic visualization for social scientists, and another is on academic library policy development. Thank you.
Thank you so much, Dr. Lamba. I have so much to think about, as I'm sure everyone does. And we're now going to move on to Dr. Li. And as a reminder, if you have any questions, please put them in the Q&A. Thanks.
I hope I'm sharing the right.
I see your slides.
Yes. Okay. Turn on the camera. Hey, thank you. Thank you for introduction and thanks Dr. Alamba introduce all the text mining. So you can see that there's so many the insight you can get from the text. And so what I'm talking and the focus that the text mining and so how can we use that in the cancer care? So I'm from MSK. I'm the chief for computer service and attending physicist. So as you can see that the recent years, especially for the past 2 years, the text mining, especially language model, large language model, has been flying and have so many use cases outside the healthcare. But as a healthcare professional, we're trying to bring everything possible to understand the cancer and then to help to treat our patient. So let's see. So I will start the couple of applications from my team and also the collaboration with my collaborator outside MSK and inside MSK. We'll start with radiation therapy. So that's the medical physicist is working very closely with radiation oncologists to treat a patient that use the high dose radiation. So the typical, the workflow is the patient see the oncologist, and then we decide to go to treat the patient put in the simulation, and then we acquire the image, and we draw the target and and then dose the prescription, and then the planning phase, and then finally plan has been done, the plan check, and then you get it delivered. So you can see that. So this is a fairly complicated process rather than give you the prescription and you take the medicine. So this is the steps, and then there's multiple teams members involved in multiple different decision making point with different data source. So fortunately, unfortunately, I think the most of the patient will be wait for 10 days or maybe 1.5 weeks to get the first delivery. So there's quite a lot of the handover and streamline data processing is done manually. So how can we use the text mining language model or large language model to help the speed up the decision making and the data collection? So we'll show that so there's multiple challenges to actually doing that. And as you can see that those days everything's digitalized. We have multiple system, multiple vendors, but digitalization doesn't mean the efficiency. It's actually, I use this word, digitally fragment data. So you have more fragment data than actually before. And even you can collect this data, and so you have to make the data talk to each other to make this digital profile or longitudinal patient record. Otherwise, the data still doesn't mean anything to the teams. And finally, that for radiation, and I'm pretty sure for other treatment, therapeutic treatment. So the team need to be communicate, between different roles. For us, radiation oncologists, to planners, dosimetrists, physicists, therapist, coordinator, nurse, you name it. So it's a fairly complete the teamscapes. So the goal is that, so how can we build a way to tell the patient story, connect all these clinical events together to help to make the decision quickly. So we started working on this 2 years ago with all the collaborations with MSK, especially medical physics, radiation oncology, and our collaborator from Digits, our IT and infrastructure department. So we start to put in some things, and the platform we call the Plan Q at this stage. And so one of the core part is that we want to connect the patient stories together. So the clinical events need to be connected. So this is a simple, the methodologies. So we do the embeddings, we extract the features from the patient notes, which is a structured, sometimes unstructured, and we do the matching. So that the AI will not be 100% matching, but we put the human in the loop. So, but in overall, you still get a pretty good patient stories. And also the business logic actually embedded in this prompt design rather than, you focus on to put together manually. So you can change the prompt and get a better matching and to follow the patient stories. So I just give one example. This is a screenshot, and we have that in the clinic right now, and since the beginning of this year. And we have, as you can see, that the patient stories we follow closely as a real-time data flow into the clinic, and we will know that where's the patient, and every clicks will have this structured data mined by using the large language model, and so we'll significantly reduce the workload from the coordination and management team. And so all the decisions will go back to the system. So we collect this as a human feedback for the future fine tune. So this has been in the clinic since February 2024, and we're seeing like more than 200 people use that daily, and we're tracking. I think it's at this time probably 7,000 to 8,000 patients through the systems. So next applications, and not just for the clinical decision making, another is that clinical risk events, right? So it's always happening, and so we collect this data. So can we build some kind of systems, what we call the instant learning system, to understand what's the clinical events and give the guidance and to the teams, how do we manage the patient, and retrospectively we can learn from the events that prevent for the future. So that's I'm working with my research assistant, my postdocs, and also clinical teams. And so we are building this AI ILS. It's an AI based the instant learning system. So we use HFAX, and so some of you probably know, some of you know, but it's a human factor analysis framework used for the aerospace. But we bring that into classify our events. So there are different tiers. So tier 1, tier 2, tier 3. So we use the data, and either the generative data and plus the real events from MSK, and we train the models. Before training, and we do the de-identification and acronym expansions to make sure that they are not have a patient information slip into the model. And so we use open source, and also based on the Llama 3.1. So I have this quick demo. You can see the system. You're going to ask the system, so we'll give you an introduction. So what the tiers you want to do the classification, and we'll see we'll go tier 1, and you start to type in the events. This is just a demo. So, but in the real production, will be hooked up with the database. As the data is coming, they do the classification. So nice things about this interactive, you can even ask the model. So what's the underlying? So why do you chose this one? And model actually give you the answer based on the learning of the model, all the data. So have a better understanding, and the model can be explainable rather than treated as a black box. Okay, next applications, and what about the clinical workflow and triaging? So this is all the decision tables, and I was trying to put together with my engineer is that how you visualize your code in some way that as a human we make a decision what's the level we should go for the initial radiation therapy triaging. So you can see it's a pretty fancy. I would say that as a human, we're doing quite good jobs to understand this, but how can we teach a computer? But we as a human, it's kind of tired to do this, and then we sometimes made a mistake. So that's we start to putting all this logic into train a large language model, and to make a decision on behalf of us with the rule and with the data from the clinic. So that's we start to do a piloting this study with the pathology, my collaborator from the pathology part, and we use the large language model, open source plus the plus commercial grade, the GPT models from OpenAI, and to do the flow cytometry triaging. So I'm not going to the details, but you can see that by reading the reading the notes, the pathology reports, and then the model will figure out is the abnormal populations. You need some kind of workup, so which lab you need to order. And then the model will decide what this is, and they're going to figure it out and set up priorities. And so you can see that. So if you tell the models how to do that, and the model became the replace of the human in the middle of decision making. The MRN tap into the system. So I have the demo as well, and it will start extract the flow cytometry notes, and then we'll decide whether you have a prior diagnosis or not. If yes, it will follow the prior the lab panel, but now they will continue to look at the pathology notes, and then this is a multiple decision making point. Finally, there's another LLM to actually give you a summarize, and then to make a decision. Or there's nothing they can make; they will pass into pathologists to make the decision as a human. So you can see that. So we want to use the model to understand more on the notes, and also the release the pressure from human and work closely. Okay, so beside all this, and I think that's some things okay, so there's one more. One more is so you are not just to make a decision, you also build the knowledge graph. So this knowledge graph can be stored somewhere else and to be answer more interesting questions, not just the clinical workflow strategy. There's another works I recently working with my collaborators, now from MSK. It's outside collaborator from UCSF. And we start to study whether we can use the large language model to understand the cancer progression and cancer trajectories. So I've just start, I copy all the things from our papers. So we train the models, our foundation models based on the open source, and then we align the models with the domain knowledge, align with the medical, and plus the MSK internal DID, the radiology impressions. So this models, and we do the benchmarks and look at the performance. As you can see that after fine tuning and align, and the model is going to be aligned with the medical domains, the performance is going to be shift from the general domain to the medical. And all this spider web map, you can see that this medical domain has been enhanced, and the scalings, it's much better in the medical domain. So once we have the model and we start to look at our internal data, and then we share the models with our collaborators and with the cross validation. As you can see that, so I would just put there with like 5 major cancer types with different patients and reports. And you can see the AUROC is a significant different than the without training. And here's the 93 by looking at smaller models, and larger models, you get 97 for all the cases. And so we share this model with our collaborators from UCSF. And so the model has never been seen and trained with outside the data. So we can see, the classification. It's a significant different than us, but it's not quite not like naive thinking. They still, you can see the knowledge has been transferred from learning what inside MSK and to the general domain, understand the cancer progression. So even further, we use the model to do the cancer trajectory study. I think that's actually similar to Dr. Lamba mentioned. It's the topic of modeling. We use llama-based language model, and we study that. So the cancer has been spread, and based on the progression, you can see for the breast, and most of the cancer spread to brain, and on the psyche notes, psyche plot. And it's very clear to see that the trajectory of the cancer has been spread to different part of the organs. So yeah, that's basically summarizing, what my group is doing, and with the applications and the data sharing and the privacy concern, because we One thing is we remove all the patient data, so we train the model, and we can share with the collaborator, apply other data. So there's no patient notes transferring over there, but you can see the knowledge has been transferred between one institution and another one.
Thank you so much, Dr. Li. That was fantastic. Finally, we have Dr. Liu.
As introduced, our research is housed within the NIH Intramural Research Program. In particular, I work at the National Library of Medicine, which is one of the institutes of NIH, and where I supervise a group of scientists and trainees working on AI and machine learning for both biomedical text and image processing. But for this particular talk, I'll be talking mostly about the text data, which includes both the biomedical literature as well as electronic medical records when access is given. So using AI and machine learning, we work on a wide range of different problems, including improving information access for the biomedical literature, which is a core mission of the National Library of Medicine as well as the NIH. Beyond that, we are also interested in extracting knowledge, information from unstructured text and turning that into structured knowledge, where we have developed some of the tools widely used, which I'm going to talk a little bit about as well. Last but not least, we are interested in working on patient data in the healthcare domain, and especially with the surge of large language models. And that's what keeps us busy in the last 2 years. One signature project is using large language models to speed up the process of patient trial matching, but this is not going to be the focus of today. So let's start with PubMed, because I think that is something that perhaps most of the audience will be very familiar with. In fact, you may have your own papers in PubMed, or you are a regular user of PubMed search engine. So on average day, we have about 2.5 million users. They're doing about 3 million searches and 9 million page views. So that makes PubMed actually one of the most widely used websites by the US federal government. And PubMed really operates 24/7, 365, even when government shuts down from time to time. So even though AI and machine learning is a hot topic these days, but in the last 18, 17 years I've been at NIH, we've always been thinking about how do we using AI and machine learning to improving user experience when doing the PubMed searches. So here is a list of search assistants that are exclusively implemented and created using computational approaches. Now, of course, these are the tools that we created. Some of them are many years ago. So this is prior to the era of large language model. So we were using something you would consider as conventional AI and machine learning approaches. But what makes it different from PubMed versus some other commercial or public search engine is that for each of the search assistant or each of these tools, we would always be associating them with a either technical scientific publication or white paper at least, because we really believe open science and we really want to making sure this is very transparent to our users. In fact, we wrote a sort of survey paper, a perspective paper, and showing exactly how we, using a layman language, describe how these tools were described under the hood, as well as how our users have been responding to these computational search assistants. Now, as much as I love PubMed, but in the end, this is still a very keyword-based search system. What that does means that the search quality of the results actually depends exclusively on the keywords you choose to put into PubMed search engine. Okay, and it does not really understand the semantics. It basically doing a matching between the keywords in the query as well as the words in the article. So sometimes for queries like COVID-19, especially during the beginning of the pandemic, we want to find information needs is I want to find all the papers, only the papers about COVID, then it's very hard to do that using PubMed search engine, because the word COVID-19 or SARS-CoV-2 were not coined or used in the literature consistently until summer 2020. And everything before that, authors and researchers are just using a wide variety of ways. Some of them are showing here to describe the virus. But arguably, that was sort of the time period. There's a pressing need for the researchers community and for the wide general public to understand this new virus. And that was basically the motivation. We created a central repository for COVID-19 papers we called Lit COVID. And it does nothing but includes all and only the papers about COVID research. This is, I always say this joke, this is a 2.5 people project, because it was basically done by 2 of my former postdocs and then some of my time. But over the years, Lit COVID, during the past 3 years during the pandemic, we really served a lot of our users all over the globe. As you can see from the world map, I think we touched basically everywhere in the world, including people in Antarctica. And we extensively used AI to cope with the issue that it's a limited manpower we have to curate all these papers. And we turn out to be AI to be a great tool that we can use to speed up this process. Now, all I talked about so far is to using AI, using machine learning, using text mining to cope with the issue of finding the literature, finding the papers to read. But these days, guess what? The main problem is not you don't have papers to read. It's the opposite. You have too many papers when you're giving a query of 3 or 4 keywords in a search engine. You are often overwhelmed by the number of papers returned. It can be hundreds, it can be thousands, or even 10,000, or even more. So it's a $1 million question. How can we actually teach computers to read the papers, understand the papers like human scientists, and then we can really leverage them to scan that large number of papers and to generate some connections that humans would never be able to do. So towards that goal for accelerating discovery, we've made some baby steps, I would say, by teaching computers to understand what is a gene in a paper. What is a relationship between gene and 2 genes? Is it gene-gene interaction, or what's the relationship between gene and the disease? Is this gene causing the disease, or this is gene drug treating the disease, or this is a drug chemical that causing the disease? So we focus on a set of key concepts in this case and the relations, because based on our early analysis of the PubMed search log, we find that most of the time people search for genes, diseases, drugs, and chemicals. And that's certainly not unexpected, because after all, these are the most important concepts in the biomedical research. So, thanks to 2 very hardworking, talented scientists in my lab for 5 different entity types: disease, mutation, gene, protein, species, and chemical drugs. We have developed some computational tools we call taggers. Basically, they can recognize the disease names and gene names, and then further store them in a standardized or normalized manner. Now, as you can see, we've done this work starting almost more than 10 years ago now, and some of the tools we have gone through multiple iterations. These tools were developed, again, prior to large language model. And you may wonder, would I just give an article, blank, raw text to ChatGPT? Would ChatGPT actually recognize that better than your tools? Well, we've done that. We've done that in a recent paper that is going to be out very soon, where we compared head-to-head comparison between these tools versus ChatGPT, and we found our previous tool still works better. So let me give you a concrete example what we mean by these taggers and what the results you can expect by these tags. So here is a blank PubMed abstract, and we have a tagger for tagging sequence variants and mutations. When you apply this tagger to this PubMed article, we will find there are 3 mentions, and these 3 mentions are referring to the same mutation. And moreover, when we have the gene information next to the mutation, we can actually associate this mutation to the unique standardized concept. In this case, we use a identifier, standard identifier in one of those widely used mutation databases. So we make all these taggers public available because, as I mentioned, we believe in open science. And what we found is a lot of the users would download these tools and then apply to millions or even the entire articles in PubMed. But we thought, why don't we actually do this for our users? Because first of all, people don't have to do this over and over again, repeatedly by different groups. Number two, there are people who may not necessarily have the computational resource or expertise to run these taggers themselves, but they still want to get the results. And that was basically the motivation and rationale why almost more than 10 years ago, we developed the very first version of a online system called PubTater. Essentially, we basically apply all our tools to the entire 30+ million articles in PubMed, and then we aggregate the genes, diseases recognized by these taggers, and then at the back end, and then render them to the front end. So as long as a user have access to internet and web browser, they can actually see the semantic annotations in a web browser, which is very important because just as you see here, none of the taggers are perfect. Now, of course, one of the arguments is humans are not perfect. If you ask two human scientists or experts to annotate the gene names, I guarantee you they have a difference in what they believe is a gene name. That's number one. And number two is that even though they're not perfect, does not mean they cannot be useful. In fact, we found it's actually very useful because we open this to all the users around the globe, and they can retrieve data look at the data using a browser. They can also write some kind of programs to access the data through the APIs that we opened. And over the years, we have had over 1 billion requests, API calls from many research institutes. I'm pretty sure that we have users at MSK as well. Now, because of the popularity, because of the demands from our users, we have actually continuously improving PubTater system over the years. As I mentioned, we started as 2012 and then as a web browser version, and then we added API access, we added FTP. In 2018, we made a bold move where we text mine not only the abstract, but also a couple million free text in PubMed Central. This is a full-length papers that I'm talking about, even though it's few million full-length papers, but they actually, in terms of length, in terms of words or characters, they are more than the entirety of the PubMed abstract, because each paper is maybe about 10 or 20 times longer than the abstract. And then in 2019, we actually improved our taggers using the more advanced deep learning techniques. And last year, first time we added not only the entities, but also the relationships between those entities. So this is what we can offer now, is that for an abstract or for a full text, we would tag in not only the entities, but also the relationships. And moreover, we will put them into a structured way that users can access them through one of those approaches, one of those ways they can, we talked about, APIs or FTP download or so on and so forth. So one thing we did not do several years ago is we only using abstract and full text. We never thought about, well, we thought about also text mine supplementary materials, but we were sort of reluctant to do that because you can guess what are the files people can put in. It's very noisy because you can have figures, you can have tables, you can have PDF, you can have Word file, you can have spreadsheets. So because of that, different file formats and so on and so forth, it makes it very noisy and it hurts the performance. Okay, but at the same time, we've had repeatedly been asked from our users, and they really wanted us to add supplementary, at least for one of the entities, which is the mutations and variants, because they told us that it's so important because a lot of the data is actually only mentioned or in the supplementary materials. So A couple of years ago, we eventually created a spin-off, I would say, called Litvar, which is mainly focused on tracking mutations in the literature. And that tool, you can looking for the variant and then also search free text. So you can put in a variant and then cancer, and then you can see what are the relationship between this variant and cancer in the published literature. And that turns out to be, and our user turns out to be great, to be correct. And this is great because we've seen this used by various labs doing the sequencing and as well as research papers over the years. So all of this was happening sort of near the end of 2022. And then, as you would know, that's also when the time that ChatGPT was launched. In my view, ChatGPT understands the language, human language, semantics better than any of the previous AI tools. And that's probably why it only took 5 days for ChatGPT to grab 1 million users compared to much longer time for some other popular online services and applications. So we were also very intrigued. I'm sure that everybody will have their own wow moment about ChatGPT when you first interact with it. And I think the beginning of 2023, we started our very first pilot study with ChatGPT. And to the same question we are very familiar with, we were thinking, if ChatGPT is so great, would people stop using PubMed? And because in PubMed, you have to find your keywords, you have to do the search to make the judgment of which paper is relevant and then read those relevant papers. Instead, can you just ask the question directly to ChatGPT and maybe you'll get the answers back without having to do all these steps I just mentioned. So we did this pilot study where we basically, because of our work with COVID, we asked, so we sort of know, have read some of the COVID-19 research, even though that's not really my expertise. But we asked ChatGPT, what are the most common symptoms associated with long COVID? And at time, this is the result that returned, even though we were not so impressed with the symptoms it returned, but ChatGPT seems to be extremely confident. And because for each of the symptoms, it will also associate with a source of evidence, a scientific research paper. But when we copy and paste those titles into the PubMed or other search engine, we find they basically do not exist at all. These are completely fabricated, and everybody knows this is a hallucination issue of PubMed, of ChatGPT these days. Now the PMIDs are real, but again, when you're looking for these PMIDs, they are associated with papers that have nothing to do with long COVID research. So at the time, people have already proposed one of the ways to addressing hallucination is using something called retrieval augmented generation, or RAG for short. Basically, instead of directly asking questions, you're trying to adding an intermediate step in between answer and the ChatGPT or large language models in general, where you would asking the large language model to retrieve summarize the relevant information from a search engine. And we tried that. We tried that approach, but instead of using a retriever system to return papers about long COVID, which sometimes can be incorrect or sometimes can be information loss, we actually manually picked 5 papers. We know all these 5 papers are relevant and perfectly contains answers about long COVID symptoms. And then we just give them to ChatGPT and see what ChatGPT can return instead, still answering the same question. And this time, indeed, as you can see, ChatGPT gives a much better answers. And using the same PMIDs that we provided to the system. But if we dig deeper, we still find there are some issues remaining. So that was basically our very first paper published last year about how ChatGPT would impact information seeking in our domain. And the paradigm that we say is that you can use it to retrieve, you can use it to summarize, but most importantly, you have to have human verification in the end, because you can't just trust that blindly. And after that, I was looking for papers related to our perspective, and we find there are actually some more concrete studies where they give some more detailed statistics. For example, in this particular paper, they showed that 31% of the reference will be fabricated when you're using that for finding the relevant papers, so on and so forth. So, so this basically is just give you an idea what type of work we do. In fact, my lab has been, like I mentioned, in the last 2 years, have been very busy with explore the power of large language models for healthcare. We've actually developed some of the novel applications because I believe, at least from my 20 years of research using AI, this is a tool that is getting us much more closer to real world deployment than ever before. But having said that, it's equally, or it's making this more important to look at the safety issue, because we want to making sure AI is used in a safe, fair, and secure way, because otherwise we would lose trust by the end users. So with that, I will close my talk, and I thank the kind invitation, and also I already mentioned some of the people who actually lead those projects that I mentioned before. Thank you.
Thank you so much, Dr. Liu. That was absolutely fascinating. We've had some questions come in, and just in the 4 minutes that we have left, so we had questions for Dr. Lamba and Dr. Li, that we've already had addressed, but we did have 2 for you, Dr. Liu. So maybe if you can answer these quickly before we wrap up.
Okay.
So the first is, how do you deal with PubMed records in PubMed that don't include an abstract? Because the title might not be descriptive enough to capture things like gene names.
Yeah, so I just answer them quickly here. And so, so that's very rare these days. In the past, there's actually a much higher proportion of new articles without abstract, but these days that proportion is, I would say, is kept as a minimum. When there is no title or there's no other information, basically there's nothing we could do about it.
Okay. And the second question was, it's asking, like, does the tagger is for biological or medical entities, is that kind of like a co-reference resolver?
Yeah, no, but so it's a more, so the taggers as input is just a blind text, and then output is the same article but with the entities tagged. So we used machine learning and AI tools for these tagging systems. Now, during that process, a module can be a co-reference resolver, because it can mention this genes. You can imagine in the abstract, there could be multiple mentions of the same entity, just like the example I showed you. So co-reference resolver, or is one component, a module of this tagging tool. Another tools that were often included as a module is abbreviation resolver. We would have the gene name and then abbreviated the name, and then we use them the long form and short form together to address or disambiguate an entity.
Oh, okay, wonderful. Okay, thank you. I want to say so much appreciative thanks to all of our wonderful speakers today. I feel like I've gone from 0 to 60 in my knowledge of text mining, but still have a tremendous amount to learn. So we will send the recording to anyone who's registered, and we will also, with permission of the speakers, share their presentation slides. I hope everyone has a wonderful afternoon, and thank you again to our speakers. We so appreciate you taking the time to educate us about text mining and other applications related to ethics, cancer care, etc. Thank you so much.
Thank you. Bye now.
Thank
Have
you.
a good one. Bye.
Thank you.